Welcome! In this video I'll discuss constraints on evolution equations. And this sometimes happens that there's a set of equations which need to be solved for a fluid or plasma, and there are some constraints which also need to be satisfied at every point in time. And some of them are satisfied exactly when it's analytical solution, but when you have solved in a numerical method there are always some errors, and those errors can accumulate and build up over time until eventually you end up with unphysical situations. And an obvious one for MHD is that you have divergence of B is 0, so the solenoidal constraint, and this is of course part of Maxwell's equations, and so it's satisfied automatically in an analytic calculation. But when you solve this numerically, you integrate Faraday's equations, or integrate Ohm's law essentially for MHD, you end up with magnetic fields which are not, which don't have this property, and so this can lead to numerical errors and I say unphysical situations in the solution. And so there are some approaches to solving this I'll discuss here. One is just to evolve the vector potential, which is a very straightforward method, but has some costs as well. There's divergence cleaning, and there's a whole family of methods which have been developed essentially to allow a small amount of error in this divergence, but to constantly try to remove that error from the solution. And then there are approaches called Constraint Transport, which try to change the numerical method so that this error stays machine precision, so it stays extremely small. And so we'll start by just outlining the pros and cons of these methods. So in general there are two approaches to these kind of constraints. So the first is just not to do anything special, and treat it instead as a diagnostic. So what you're doing is using this constraint and measuring it and using it as a test for how good the solution is. So essentially you look at you run a simulation, you look at your outputs, and you calculate divergence of B. So you calculate divergence of B over time, and what you'll find is as the simulation evolves, divergence of B will increase, and so this will be like divergence of B, some kind of measure or average over the simulation. This will be time, and what will happen is, of course, starts out 0 in your initial conditions. It'll gradually grow, and then typically it'll do something like this, and then you get some unphysical behavior happening. And so this will start out very small, but you can set some kind of tolerance level. Of course, this is somewhat arbitrary, but you can set either let's say 10 to the minus 4, 10 to the 5, whatever level you're essentially comfortable with, and this will say beyond this point your simulation is no longer valid. So that's one way of doing it. The problem is then, what do you do when this happens? About all you can do is stop the simulation here, either try to clean the solution so that you restore divergence of B, or increase your resolution, so decrease your errors. And so if you have a higher resolution grid, your numerical errors should be smaller, and so this should essentially grow at a reduced rate, but eventually it will still increase and blow up. So this will be a higher resolution. And so typically higher resolution gets you longer. The simulation can run for longer, but eventually it will still blow up. But this gives you one kind of diagnostic. The second approach is to try and do something about constraining or stopping divergence of B, is ensuring that it stays 0. So you basically try to ensure that this is below some kind of tolerance. So there's some kind of small tolerance level, which again you have to set in some cases. So there might be some parameters you can adjust. So in the divergence cleaning, for example, there's a cleaning parameter which determines essentially how fast the errors are removed. But if you make that very quick, it will stop your simulation from running. So it will constrain the time step. Whereas if you make it small, then the error will become larger. So there's a trade-off in how small you can make this parameter. The downside of doing this is that you can no longer use it as a diagnostic. So because you're essentially forcing this to be 0, you can't really test this and see whether it is 0 and use that as a diagnostic for how good your simulation is. You should still monitor this and still test it to see if your cleaning method is working, but it's no longer a good diagnostic for when your code is breaking or not giving accurate results. So assuming you want to do the second case, so you want to try to clean the divergence of B or somehow ensure that it doesn't grow, there are these 3 methods. So there's the solving the vector potential, there's the cleaning methods, and then there's constraint transport, and I'll cover each of these in turn. So we're essentially evolving an equation in time which is of this form. So we have so this equation we're evolving for B. So B starts, divergence of B is 0, but then small errors in this quantity build up. What we can of course do instead is just write that B is curl of a vector, which is the vector potential. And so now we evolve equation for A, and then at every time step we calculate B. So we have dA by dt B cross U is 0. So every time step we integrate A in time, and then every time step we can calculate B from curl of A. So there are some costs to this. So if you do this as 2 steps, that you first calculate B by using this, so you differentiate A, and then later you have to differentiate B in some of the evolution equations. This then requires more communications if you're writing a code. If you substitute A into all the other equations, you end up with second derivatives and more complicated expressions for the fluxes in terms of A. And so you might there again have to change the numerical method slightly, or have more communications to do this differential of A to get B. But in general, this is quite a robust method. It's used for particularly things that reduced MHD models, typically evolve A rather than components of B. Quite common in astrophysics is the second method, which is cleaning, divergence of B cleaning methods. So there are many different ways of doing this. There's a whole family of schemes, but essentially the idea is to have an equation for divergence of B, and have that either a hyperbolic, so advection equation, or a diffusion equation. And so if there's some error at one location, you spread out the error and you diffuse it towards the boundary and out of the simulation. So you have a local error in B, and say we have some steep gradients or some other things we're looking at which produce an error in B, and then these methods spread that error, so diffuse it and advect it out of the domain, typically to the boundaries. And so we're evolving the same equation, so we have dB by dt plus divergence of B cross U. That's a U, which you might also write as in a slightly different form, particularly if you're writing a finite volume code, then this can be written in a quite useful form. So we have now a divergence of a flux, because this is the form used for all the other equations. So when you have conservation laws, you end up with a sort of d by dt of some quantity like momentum or density, and then a divergence of a flux. And the flux for this magnetic field can be written as this UB minus BU. And this is a dyad, so it's 2 vectors next to each other, so it has 2 indices. If you prefer tensor notation, we can write this out. So you see this divergence of this dyad is just differentiating both, but the dot is with the first vector here. So this differential here is dot producted with this first index here and the first index there. And so this is a divergence of a flux, which can be solved using standard hyperbolic methods. But whichever method we're using, either solving this equation or this equation, we essentially add a term to the end. So So you end up with, so we add this extra term in here into the equation, and then we add another equation for this psi. So we have an equation which in general for the mixed, so-called mixed method is like this. So you have a time evolution equation where the CH is a hyperbolic term, which is a constant you can specify. So it's a free parameter, not a physical quantity. So you see it's an evolution equation. So it's in general has a hyperbolic term and what will turn out to be like a diffusion term, which has a source term, which is the divergence of B. And so whenever divergence B is non-zero, this psi will change and increase or change in time. And we'll see that when substituted into here, this will actually end up cleaning the field. So if we take divergence of this first equation, so divergence of a curl is identically zero, although I say it may not be in numerically, but here we have, so d by dt, we're taking divergence of B. The second term here is zero, and then here we have divergence of grad psi, so the Laplacian of psi. So I want to substitute in this into here, so we take the second derivative of this equation. Now, if we say ignore this term to start with, so we just have Cp goes to infinity. So then we have this term. So then we have this term here. We just substitute into there. And you can see this is a wave equation. So we have the second derivative of divergence B on the left hand side, and we have the second spatial derivative on the right hand side, and the ch is the speed, the wave speed. And so this term will advect or move any errors in divergence of B at the speed ch out of the domain towards the walls or boundaries of the domain. If, on the other hand, ch goes to infinity, so we essentially remove this term here, so we just have this term. Well, in that case, we can just substitute this into here. So if I'm ignoring this time derivative, I just substitute this term into here, and we end up with a slightly different equation. I see this has the form of a diffusion equation. So now we have a first derivative of grad B, because it's just taking this equation here. Thank God here. So I substitute this into here. This is the first derivative. This equation just becomes this term here. And now I have a diffusion equation. So it's a diffusion equation for divergence B, and this will diffuse the error and spread it out. And so generally you have a combination of these two terms, so a diffusion term and an advection or hyperbolic term, and the combination of these can keep the error in divergence of B small. So lastly, I'll discuss the constraint transport method. So there's this reference here from 2006 by Frommang, which is also on archive. So it's Astrophysics 0607230, which describes this method and applies it for astrophysical problems. So the basic idea is to use a staggered grid system where not all the quantities are defined on the same points. So usually in finite difference methods, most methods of hyperbolic systems, all the quantities are defined at cell center. So if these are the cells that the grid is made up of, typically everything is defined at cell centers, and then fluxes are calculated at cell edges. What this method does is it defines the B field and the E field at different points. So I define, let's say, the B field. So the B field here in the x direction. Let's say I'll label this direction here y, and that direction x, horizontal. And now the B field is defined at the faces, at the point where it's normal to the face. So the x B field is defined here, where it's perpendicular to the surface, and the y is defined at the top of the box. So here you have Py, and Bx is the horizontal here. And the idea here is to make Maxwell's equations identical. So you can, instead of solving the differentials, you solve the integral form of Maxwell's equations. And so one of the induction equation essentially becomes this. So you have the time derivative of the flux through the surface. So it's B dot ds. This in general here it's a 1D because it's just a line, but in 3D it would be a 2D surface. So you're integrating over the surface of the cell, and that's of course just the loop integral of the electric fields around the outside of the surface. And so in this box here, what we'd have is if x and y are in the plane, E is defined here. In here it's the corners, but in 3D, which I'll draw shortly, it's on the lines on the edges. So here this would be EZ defined here. EZ. And so end up with fields defined on the surfaces and the electric fields on the edges. So I'll try and draw this in 3D now. So I'll draw a 3D box, which is the cell. Okay, so we have a 3D box like this. So the magnetic field is perpendicular to the surface. So here we have a component here. So if I label this direction as x, for example, the vertical direction is y, this direction z. Let's just make things clear, I'll put z the other way, just to make the drawing easier. So this is in the x direction. Here we have a surface, and so Bx is coming out of the surface at right angles. By is defined at the top surface, so By is coming out through there, Bz is coming out through here at the front. So they're all three of them are orthogonal to the surface. And this makes integrating over the surface very easy. At least first order is just multiply the magnetic field by the area, and you have the flux. And then if you want to do this loop integral, you need to know the integral of the electric field around this path here, around the edges. And so here we define the electric fields, so Ex is defined along the boundary aligned to the x coordinates. And then like the x direction, the Ey is on the y coordinate, at least the side of the box that's aligned with y. And then Ez of course is also on here, so Ez is over here. And Ex. So now if we need to do, say calculate By, so on this top surface, we can integrate along these lines, the edges, integrate the electric field to get the integral, and then this gives us the flux, change in flux through the surface. And because you use the same values of Ex for calculating each of these surfaces, the divergence of B is conserved at least to machine precision. This is also a quite widely used scheme for electromagnetics. So if you're just evolving the electromagnetic field, say following waves through a system, what's quite often called the Yee cell. So if you look up Yee cell or just the finite difference time domain, TD method from electromagnetics, has some downsides. So one is now because the magnetic field is defined at different points, so each component of the magnetic field and the electric field are defined at different locations. You need to do more interpolations. And this can then introduce an error in the energy conservation. So see, each of these methods has some advantages, some disadvantages. In each case, it's a matter of making the whole system work efficiently and accurately. But there are always some trade-offs in choosing the perfect method.